let's come to the buoyancy and resting fluids. To explain the effect of buoyancy, it is important that you have to know fluid properties, and in fluid properties you've learned that the density will change with temperature and pressure. And so if we have different objects with different densities, you will have the effect of buoyancy. So what is buoyancy? Buoyancy is the main principle why balloons or airships flow, or why wood in water will float on the surface of water. Yeah? If you have something that is lighter, yeah, you have a lower density in one liquid or in one fluid. For example, if you have a balloon, you have hot air inside, or you have hydrogen inside the balloon, then the fluid inside the balloon is lighter, and if you have air or so outside, it will flow upwards. So you have a force depending on the density difference times gravity constant times volume. And this principle was first discovered by Mr. Archimedes from Syracuse. He lived around about 300 years before Christ, and he was a great inventor, and he developed a lot of interesting objects. And so the principle of Archimedes, the effect of buoyancy, is called principle of Archimedes. And Archimedes, he was a great scientist. We know a lot of mathematical formulas from him, but one of his main interests was not to build formulas we can use today. He was interested in practical aspects of his science. For example, he invented pump systems. Yeah, this like called also Archimedes snail. You can pump up water, or there is a, we do not know if it's really true or if it's a tale. It was written that he invented a big iron claw to catch the ships from the enemies on the seaside. Or here he has written some documents where he described that he invented a big mirror to focus the light of the sun on different ships and let them burn down. Now we do not really know if this is true, but it's truly proof that he invented, that he, let's say, examined the Archimedes principle. Okay, and here you see the Archimedes principle described. We have a liquid, for example water, and that's some fluid property you should always remember. How much is the density of water? The density is around about 1000 kilograms per cubic meters. And that's always a question I ask you. Density of water, that's the first important thing you should know. And in the last chapter we have seen, if we now have, for example, diesel or oil, oil has a lower density, about 1840, it will be over the water. Yeah? And what happens if we have an object, and let's say a wood chunk or a block of wood, if you place it on the water and the density of the wood is lighter than the water, then we will get a force upwards. And of course we have a force downwards, so gravity, mass times gravity constants, that will go into opposite direction. So if the force that pushes the wood chunk upwards, yeah, is higher than the force, than the gravity force, it will float. If it's more or less the same, if the density of the wood, we can have really heavy wood types. Some woods are heavier than water, they will go down. Or if you have for example, a block of lead or metal or steel. Steel has a really high density, about 7,850 roundabout density, and this is much higher than 1,000 kilograms per cubic meter, and then the block will go downwards. Okay, and if you want to get a little better explanation, maybe I always advise you the tool GeoGebra. I placed the links on the slides of a GeoGebra example, a GeoGebra explanation, where you can go with the mouse to this block and change some forces and look what happens. Okay, it's an animation. Okay, here is also, yeah, more or less the same, and in this slide I ask you, why would the body swim? Okay, I think I already explained it. If you have a body, for example, a ball made of wood or a wood log or tree log, then you have always a force upwards, and the force upwards depends on the density difference of the wood subtracted by the water times gravity times volume, and we will always have a gravity constant upwards. And now it depends on the body will float, yeah, will partly float if the forces are upwards are higher than the forces into gravity direction, and the body will sink down into the water if the gravity forces are higher than the forces upwards, the floating forces. Okay, that's a principle, the Archimedes principle, more or less. And okay, I think it's more or less a force balance. Okay, so here again, why will a body float? Here the formula, please, from the Archimedes principle, please always remember it. The resulting force is gravity times volume of the body, and times difference between gravities. And if the resulting force is higher than 0, the body will sink down. If the forces are in a balance, yeah? If the forces downwards and upwards are balanced, the body will swim. And if the resulting, or let's say not swim, it will float in the water. And we have assessed if the force is lower than 0, the resulting force. Okay, I think that's something you should keep in mind. Okay, let's come back to the same principle. And I told you during the lessons, I always want to introduce some famous guys, some famous scientists, some persons that were important for fluid dynamics, important inventors, and in many cases, these persons that invented a lot, that did a lot of mathematics, that did a lot of physics, a lot of fluid dynamics. In many cases, they invented also other things, and sometimes they're also known for other inventions. For example, Mr. Bernoulli was specialist in fluid dynamics. He came from Switzerland. He was interested in flow of rivers and fluid flow, but Mr. Bernoulli invented a lot of other formulas, or Blaise Pascal. He was a scientist, he was interested in mathematics, but also in fluid properties and fluid dynamics, and for example, the pressure is named after him. And here is I also already mentioned Archimedes from Syracuse. He was a famous person who, and we now named the Archimedes principle after him. And here's another guy, Mr. Descartes. Yeah? And Mr. Descartes, René Descartes, he lived about 400 years ago, and he was like Galileo, also a famous French scientist, and he invented a lot of laws and made mathematical proofs. And today, Descartes, he was today we know him a bit better at Cartesius. Maybe you've heard of Cartesian coordinates. Yeah. In this time, the scientists always try to use Latin names. Yeah, they build the Latin names after their French names or German names. Okay, or English names, of course. So, and what has he done? He invented something similar to a submarine. Yeah? Even in this time, the people have problems. They want to search for treasures from sunken ships or anything like this. And he invented a submarine-like vessel. Yeah? You can see it here. It was built of iron or so. And it was possible to push it under the water and keep the air inside the vessel. Yeah? So it was also possible for people who dive with this bell-like object. And you could imagine it is pretty much dangerous. Yeah? But it was a possibility to work underwater. Yeah? But if you want to get a bit more details about it, there's a really good book called the Foucault's Pendulum, and here they use it. Okay, so but let's come back to Mr. Cartesius or Mr. Descartes. He worked with hydrostatics and with fluid properties of air and water. He invented this vessel, and he also some other thing I already teach you is named after him. Please remember the Cartesian grid. Yeah? Structured, I showed you what is a structured Cartesian grid, and that's a really important topic, a really modern topic nowadays in the age of digitalization and computer simulation. I already showed you we can use this Cartesian grids today with ANSYS CFX to calculate fluid flow problems. And the name Cartesian comes from Mr. Descartes. Okay, there I think that's something you should know if you work with fluid dynamics. And please also remember, if you work with ANSYS, there is a possibility to use structured grids. Structured grids are mainly in the Cartesian coordinate system. But we can also have other grid types in the Cartesian system. We can have so-called unstructured grids, or here you see some unstructured grids, or tetrahedral grids, or prism layer grids, and they look quite different. And maybe in the next lecture for ANSYS CFX we should have a look at these structures. Okay, so, but let's come back to the maximum displacement work. I showed you the example of the Archimedes principle. We need density differences, and here prepared a short example, please refer to the slides, look at it, check it, use it a bit. You will also need this knowledge in the exercise later. So, here's also the solution to calculate some forces. I think I don't have to read everything. You can refer to the slides and have a look at this calculation.